All right. Hey, folks. Emily Weber here from AWS. So today, we're going to learn how to use pre-trained foundation models. So first we learned what foundation models are. Then we learned how to pick a foundation model. And today we're going to learn about how to use pre-trained foundation models, notably through prompt engineering and then for fine-tuning. So let's get started. And so today's activities, so again, we're going to start with all the shots. So with 0 shot, single shot, a few shot prompting, we're going to really understand those. We're going to dive into them, explain the topics, and get used to them because they're really important ones. We're going to learn about instruction fine-tuning, what that is, why that matters, how to do it, or mostly just how to make sure that your model has done it. And then some ways of using instruction prompting techniques. We'll look at fine-tuning. So there are many different fine-tuning ways, fine-tuning techniques, and then we'll close it out with a hands-on walkthrough of using, again, SageMaker Jumpstart, the foundation models therein, to perform all of these tasks. So let's get rolling. And so say you found your foundation model. Say you finally picked the foundation model after you learned about what foundation models are. You learned how to pick your foundation model. So right now we're going to dive into parts 3 and 4. So again, prompt engineering, which is going to let you more easily construct the prompt and get the response out of the model. And then we'll look at fine-tuning. In this class, actually, we're going to have a separate video that's just about retrieval augmented generation. So there are a lot more techniques that are going on with RAG. It's a really helpful, really useful technique, but we're just not going to cover it in this one. We'll just do a separate video for that. So you've got prompt engineering, fine-tuning, that's for this class. Application integration, super important topic. Where you can learn about LangChain, for example, how to host LangChain, how to build different plugins and then point your plugins to your LLMs, all sorts of good things. Again, later in the class, we'll learn about human feedback, and then we're also going to learn about pre-training. And so right here, we'll just focus on these two. So first off, let's say we're new to this. What is a prompt? Let's see if we can just understand a prompt here. So a prompt is really your input to the model. Your prompt is what you are sending to the model. We used to call this an inference request. You can call this a payload if you're thinking about it as an API call. But in any case, it's what you send to the model. It's your prompt. And so your prompt can be all sorts of things. So if your prompt was, tell me a story about a little girl riding her bicycle, send that to your foundation model, and you'll get back some beginning of a story. You could send it, why was 6 afraid of 7? And your model will say, because 7 ate 9, or something like this. You could ask it, what is the airspeed velocity of an unladen swallow, if you're going for the Monty Python reference. And then if it's a clever model, it'll ask you African or European swallow, but it may just not get the Monty Python reference. Or you could send it to a vision model, say Big is Small by Georgia O'Keeffe, and then you'll get a response. So in any case, your prompt is all of these things. Your prompt is what goes into the model, and your response is the result of the model. It's what comes out of this foundation model. And so now that we know what a prompt is, what on earth is prompt engineering? So there is a massive spectrum of prompt engineering tasks, and generally prompt engineering is the practice of working on your prompt until it's awesome. And so that's eventually you want to get to this place where you get just a perfect answer from the model on your first try, right? Where you just pop in your question and you get this perfect response. And this is the experience you want to give to your customer, right? You want your consumer of this application, your customer, to have this easy breezy, really lovely experience. They ask a question, they get an answer. Simple, streamlined, delightful. You might use and develop what's called a prompt template. So a prompt template is basically, it's just a little file that's set for different prompts and different downstream tasks. So like if your customer is asking to summarize a record, your prompt template might have an example of summarization in it. It might be performing single shot or few shot learning on their behalf. If it's doing classification, you might have an example, etc. So prompt templates are a way that you can do this. While you're building your way up to getting that prompt template, you might just do a lot of syntax hacking. Like you'll just figure out what this model is, what syntax it's preferring. Like, does it like the word agent? Does it like the word human? Does it like TLDR? What sort of syntax is it preferring? Zero shot, and we'll dive into this throughout the class here, but so zero shot means you just send it the instruction and it responds. Like it means you don't really have anything else in the prompt. That is different from what's called single shot and few shot learning. I use the word learning here because it's mimicking learning. I don't like that actually because it's not updating the parameters, but it's mimicking the appearance of learning. So we call it single shot and few shot learning. But in any case, single shot means I take my prompt and I'm going to give it one example. So I put one example in the prompt and then I give it the body and the instruction and it responds. Few shot just means I have more than one prompt or more than one example. So if I want to have my model translate to a different language, or I want it to do some nuanced summarization or some nuanced style transfers, then I would do few shot learning. So I would have a couple examples in the prompt, plus the body, plus the instruction, and then boom. Prompt tuning is a very complex technique that you can do if you want to, which actually lets you like train vectors. So then you're generating these vectors and you're training the vectors using backprop to create these vectors that are task specific. We're not going to dive into that today, but you can. And so obviously on the far end of the spectrum is pure exhaustion, just trying everything until it works. And so we want you and your customers to be up here as much as possible. So let's see how we get there. So first off, it's helpful to know that an instruction-tuned model is going to make your life a lot easier. So you don't want just a generic LLM, a generic large language model. You don't want to just work with generic GPT-2 or generic GPT-3. That is because they haven't been what's called instruction tuned. So instruction fine-tuning. And instruction fine-tuning refers to sort of taking an instruction like tell me a story or generate a response or explain something to me. And then we have it give the answer. So it just provides the answer. You can perform supervised fine-tuning on these instructions. We're going to dive into that. But I'm mentioning it here because you want to make sure that the model you're using has already been instruction tuned. Like, pro tip, make sure your model has been instruction tuned. If it hasn't, your battle is going to be a lot larger. So here's some befores and afters. So before instruction tuning, my prompt is like, why was 6 afraid of 7? Just for fun. And so then my answer, which is from GPT-2, is totally nonsensical. Right? I'm reading this. This makes no sense. Clearly, this is not even answering this question. And then for another prompt, say the prompt is, again, this is my favorite one. What's the difference between a mimosa and a samosa? So I like this example because it tricks computers, because the tokens sound somewhat similar, but we humans know that they come from like very different parts of the world and very different sort of cultural contexts. And so it's a good test for a computer. And so what's the difference between these things? And not only does this answer not make sense, it's actually hallucinating a word. It made up this mimulating color. Like, yes, I too like to mimulate. Like, that makes no sense. So it's not only is it bad, it's hallucinating a word. And so then now we're going to use AI21 Jurassic 2 Jumbo Instruct, and let's see what we get. So the answer here for this prompt, let's read this for a second. Yeah. So this looks feasible, right? It is likely, it is a mnemonic device to aid in the memorization of the order of the numbers from 1 to 10, expression 9 on 10. There we go. So that's an answer. It's funny though, because it's still not answering the joke. Like I would prefer for it to just answer the joke, but we get some answer. And then the difference between a mimosa and a samosa. Here we go. Mimosa is made of champagne and orange juice, while samosa is a savory type of Indian pastry with spiced vegetables or meat. Both words have close. So both words have mosa in them. They have that mosa 1 or 2 tokens. So almost got there. But yeah, so obviously better, right? You can see that this is much closer to the right answer, and this is just sort of nonsensical. And so part of this difference comes from the model just being larger, right? AI-21 is just larger than GPT-2, but it also has to do with the instruction fine-tuning, and that makes the model respond much more quickly. So generally, try to use instruction-tuned models. So I'm saying this because when you start with your prompt engineering, you want to understand the model you're working with. You want to know what model it is, where it's coming from, has it been instruction fine-tuned? And if your prompt is just wildly off, then go make sure that your model has been instruction fine-tuned. And so what is instruction fine-tuning? Again, it uses supervised learning to adapt the model behavior. So you might develop a data set of prompts and then answers. So something like, how high is Mount Everest, the largest ocean in the world, how many human languages there are, and then you'll get, again, answers to the prompts or responses, and then you just put this into a supervised fine-tuning procedure. So you take your labeled data set. When you're doing this, make sure you start with a model that hasn't already been instruction fine-tuned. That you want to start with a model base and then perform your instruction fine-tuning on top of this. So that's helpful to do. But basically, it ensures that the model is then capable of following instructions. And it unlocks these other instruction tasks like translate, summarize, extract. And so instruction fine-tuning is almost how your foundation model is able to learn and accomplish so many different learning techniques. Like the foundation model learns a lot of those naturally occurring tasks in your data set just because they're there. But then when you add the instruction fine-tuning on top of this, it like makes them immediately more accessible and more useful. So instruction fine-tuning is super useful. And so your best case scenario is zero-shot prompting. And so this is what you want your model to do, and this is what you want the customer experience to be. So you want the customer experience to just easily, I ask a question, I get an answer, I get on with my life. You might do some work to get there, and we'll poke at this. But so zero-shot prompting is where you send in a prompt and you get back an answer. So my prompt could be like, what are the basic ingredients of nachos? And then I get back this detailed answer about nachos or a delicious food developed in Mexico City in the 40s. Basics ingredients are tortilla chips, cheese, and jalapeno peppers. And in the US, we like to add guacamole, sour cream, salsa, and sometimes ground beef. They're usually an appetizer, come before the main entree, can be served in the primary meal, like for Super Bowl watch parties. So you get this nice answer about not just what are the basics ingredients of nachos, but sort of this larger context for it. And then similarly with Stable Diffusion, we send in this prompt and we get back this awesome image. So in a perfect world, your prompt looks exactly like this. It's just one question, 0 shots. We say again, 0 shots because there aren't any previous examples in this prompt. It's just 0 shot. You just send it the question and you get your answer. We're going to compare this with single shot and few shot prompting. So your alternative, one alternative is called single shot prompting. So if 0 shot fails, you're going to try to add an example to the prompt of what you want that model to produce. So in my prompt, like let's say I want my prompt to give me a main course suggestion. So I give my prompt, say I give it an appetizer, which is spinach dip, generated by our Stable Diffusion. So I give it the spinach dip, and then my main course, and I want the model to sort of answer. And so you can see there's this blank here, and I want the model to just fill in the blank. In a single shot world, I add an example of this to my prompt. So I actually put in my prompt, I literally say appetizer, samosa, main course, saag paneer. My idea of perfection. So yeah, so you put both of those in the prompt, and then you get back this answer. And so we call this, again, single shot prompting, because we're providing exactly one example. So we have exactly one shot to the model. So that's single shot prompting. And then few shot prompting is where we'll add multiple examples to this. So my prompt, I could say data analysis, pandas, statistical machine learning, sklearn, deep learning, PyTorch. You Python developers will know that this prompt is basically mapping something you need, a task, and then a Python open source toolkit, a Python package that you can use. So pandas is a Python package we can use for data analysis. sklearn is a Python package for statistical machine learning. PyTorch is the same thing for deep learning. And then Django is the same thing for front-end development. So this is what few-shot prompting looks like. It's where we include like multiple examples in the prompt of the like call and response, the input and the output that we are giving to the model. And then we hope that our model will learn from these prompts and answer in kind. So again, we call this few-shot prompting because we're adding multiple examples to that model. And then because, of course, here is this cute panda bear generated by Stable Diffusion in the wild, close-up, photorealism, realistic. Yeah, and then the negative prompts are handy here because I told it to not do a cartoon and not do animation, but give me like a photorealistic panda bear. So I thought that was fun. All right, so here's an example of how you can use prompt engineering to solve summarization. Now this is a wordy slide, bear with me. So the best way to work with prompt engineering is to just paste the entire document into the prompt, like your entire PDF. I mean, based on the token size, how large your model can accept. But yeah, just take the entire document that you want summarized, paste that thing into the prompt, and then include a single instruction at the bottom of the prompt. So in this case, I pasted in some paragraphs about pugs, about pug dogs that I got from Wikipedia, pasted these things in here, and then we see this prompt. So the pug dog is from China. Physically distinctive features of this wrinkly, short-muzzled face, curled tail, brought from China to Europe, known for being sociable and gentle companion dogs. And so that's the article that I want summarized. And then again, here's my instruction. I'm just adding the instruction at the bottom of the prompt, and I just say summarize. And then the model responds with a summarization of the article. So the pug is a distinctive breed of dog. It's from China, known for its wrinkly face, curled tail, compact body, brought to Europe in the 16th century. Fact check, yes, 16th, got it. Gained popularity in Western Europe. Fact check, yes. Including among the British royal family. British royal family, yes, here we go. Queen Victoria, royal family. Pugs are sociable and gentle companion dogs, check. Described as even-tempered and charming, check. By the American Kennel Club. Did we? Yeah, American Kennel Club, there we go, great. Continue to be popular. So what I was verbally doing right there is I was doing fact-checking. I was verbally fact-checking content generated by the model, and then just literally making sure that it was in the prompt. So this is a way that you can add your own like fact-checking to the model response to sort of mitigate the hallucinations. It's just look up terms like all of the odd or notable entities or terms that this model is producing from its LLM brain of causal language modeling loss, which just predicts tokens. Just run a fact check, like just entity extract the entities from here using NER, any NER package, extract those things, and then just do a quick check, like, did it make up British royal family? No. Is the royal family in here? Yes. It's interesting because, so here it's summarizing, obviously, British royal family, because in the prompt, we said United Kingdom, Queen Victoria, which she passed on to other members of the royal family, and then here clearly it's summarizing. So it's summarizing by saying the British royal family, whereas the word British actually didn't even appear in the prompt. So that's good. That's good behavior. So when you're doing the fact checking and the term checking, you want to give yourself this like semantic meaning, like semantically, does it have that in the prompt? And so that's an easy way to mitigate some hallucinations in your model. And of course, here is your pug dog. So I did an adorable pug dog with Queen Victoria, #PugLife. I thought that was super cute. Now, I didn't get Queen Victoria in this image, and I tried it a couple times, like with different seeds, but I still love it. Like it's still just so perfect. So I thought I'd keep that for you. All right. So now we're going to learn how to use prompt engineering to solve classification. So this might sound straightforward, and it is, but let's make sure we capture this. So same as last time in the one you previously saw, we're going to take all of the relevant information from the prompt, and we're just going to paste that into the model. So all of the information from the document that we want classified, everything we have that will fit in the token size of that model, paste it in, and then ask a question at the bottom. So here we're asking, what type of bear is this? And then the prompt is long and detailed, right? So the prompt, this bear has a large round head with fluffy rounded ears, broad flat nose, small round eyes. Bears are known for their ability to climb trees, opposable thumbs, generally solitary. And then this is the obvious one. Sedentary lifestyle, spending around 18 to 20 hours a day sleeping or resting in the safety of tree branches, primarily nocturnal. And so we're describing this bear, we're describing this character, and then we ask the model, what type of bear is this? And then the model should say, oh, it's a koala bear, or koalas. And so that's how we can use prompt engineering to solve classification, right? I just paste in all of my data about whatever object or widget or timestamp or digital extraction or action or person or feature or literally anything. Like, paste all the information that I have about that, pop that in the prompt, and then get back an answer. And it says, oh, okay, great. It classified it. Obviously, it classified it correctly. And so that's how to use prompt engineering to solve classification. And of course, I also had to give you some koalas. So here are koalas climbing this tree. This is funny because the koala heads are adorable, right? Obviously they're cute, but like the legs are all over the place. Like, check this out. We've got this like ghost arm that's up here, and then some very strange looking hands. And then I'm pretty sure koalas can do this like cross tree split. Like, maybe they can, but that seems a little odd. And so it's interesting, right, as we look at vision, just to see like, they're good at some things and like really struggle with some other things. And so obviously things will get better over time, but it's still fun to check. All right. And so now we're going to use prompt engineering to solve translation. So we looked at prompt engineering to solve summarization. Then we looked at it to solve classification. Now we're going to look at it to solve translation. Same flow that we've just learned. Like, we're going to paste in the text to the prompt. So we paste in the text, which here the text is like, I parked my car in the driveway, took out the trash, put my umbrella in the trunk. And then the instruction that I gave it was to translate this into British English. So now we're going to translate this prompt into British English. I love this. I parked my car on the drive, took out the rubbish, and put my brolly in the boot. So brolly is indeed not hallucinated. It's, I want to say, from World War II, something like this, when like umbrellas were distributed by the government. I think, I might be wrong. But in any case, clearly it did translate this to British English. And so you can use prompt engineering to solve translation. And then my pro tip here is that you can use this translate instruction to solve a variety of things. So you could say like, translate this Python code into Java code. Translate this COBOL or Fortran code for you out there into Python. Translate this C++ code into Python, or back and forth. Obviously, if you're doing code level translations, you probably want to fine tune that thing or fine tune the model, but it won't be bad. It won't be bad right away. And then, of course, here is your British flag waving in the wind in London, which looks a little bit more like a take, like a Stable Diffusion's take of a British flag. Like, no doubt it can get another one if I had like increased the guidance scale to get a more obvious. Also, just in prompting for images, if you have an image and you want to just send it, you can do this really nice like image to image prompting. So a different way of doing this would be like, I give Stable Diffusion like a picture of a British flag, and then I run the image to image process, and then it like literally takes that and then generates a different background, or like puts it in a different modality or a different spot, but it's still literally the same British flag. I still like this picture, this like creative interpretation of a British flag. When all else fails, so once you've exhausted the fine tuning, once you've actually tried your zero shot, your instruction fine tuning, your few shot, single shot, all the shots, you've tried all of this, then fine tuning is going to be a good place to start. So prompt engineering is with a good foundation-based model. Like theoretically, that should do something valuable for you. That should improve the quality of your model in some meaningful way. It's expected that prompt engineering with a good foundation model will do this. The question is, will prompt engineering do enough, right? So there's this gap between how well prompt engineering improves your performance versus what your customers want, and fine-tuning is a good technique you can use to try to close that gap. And so fine-tuning is also helpful because you can create a new model artifact, right? When you do fine-tuning, you're actually creating this asset that, particularly when you use an open source model, literally belongs to you. And so it's your IP, it's your asset. You can put it and run it anywhere you want. This is an example of, it's called Dreambooth. So Dreambooth is a fine-tuning technique that, as I was just describing, does image to image, and then it sort of enables prompting on this. So it actually fine-tunes this model. So we'll upload pictures of our corgi or any dog or animal that we want. We upload like multiple pictures of the same object, right? So I take multiple pictures of my corgi or my accelerators or my plants, and then send them to my model. Then I'm gonna fine tune the Stable Diffusion model on those like 4 or 5 images. Then I can prompt it. Then I can give it prompts. And here the prompts are like, in the Acropolis, in a doghouse, getting a haircut, swimming. Like, they're actually good, right? Like, it's obviously the same dog. The dog still has this little like white, stream down the top of the head, clearly 2 ears, no hallucinations on the paws. Like, all of the features of the dog are very closely maintained. And then the dog is very realistically in these different settings. Like, the lighting is the same. The positioning of the dog is natural. The focus is logical. And so yeah, fine tuning is a great way to take new data, pop it into your model, and then get it to do something that you care about and where it performs quite well there. And so what is fine tuning, you ask, with bated breath? So fine tuning is a technique that you can use, again, to adapt a model. And just like we learned with prompt engineering, there's a massive spectrum of fine-tuning techniques. And on the plus side, we want to create a net new model that solves every problem perfectly. And if we want to avoid doing a lot of work and getting nowhere. That's the negative. And so closer to the perfection spectrum, parameter efficient fine-tuning is a technique we're about to dive into that lets you take your LLM and then you're going to inject trainable weights into that thing. So you're going to take a massive LLM that's like a couple hundred GB on disk, multiple instances just to hold it in memory. But then you're going to just inject these trainable weights into that, which will let you train just those weights. So it's extremely parameter efficient. One technique for doing this is called LoRA, low rank adaptation, which will find the ranks or find the aspects of the model that are being sort of underutilized and then do the tuning there. Prefix tuning and LoRA, those are both techniques available through the Hugging Face library, parameter efficient fine tuning, that implements both of these for you. Those are both generally a part of this larger school that's called transfer learning, where transfer learning lets you take a neural network, pop a few more layers on top of that network, and then just train those. So transfer learning is much more compute efficient, much more data efficient, because instead of needing to fine-tune the entire model, you can then just fine-tune a few layers, which means you can do it with smaller data samples and less resources, which is great. And then classic fine-tuning is just fine-tuning the whole thing. So you might, well, actually not quite. Classic fine-tuning is you take your BERT pre-trained LLM or pre-trained language model, and then you add a head to it. You add like a text generation head or a text classification head to this, and then you just fine-tune that classification head. So that's a type of transfer learning. But because you're still changing the output layers of the model. And then continued pre-training is a really cool technique you can use when you have unsupervised data. So when you have a couple tens of GBs, maybe more, of data on disk, you can take your neural network, take your foundation model, and then continue to pre-train that. And so what that means is if you're doing like a causal language modeling loss, where it's just predicting the tokens, and you run that on your data, it will learn how to predict the tokens in your data set really well. It will learn the syntax of your data set. It will learn the styles, the characteristic. And so when you do that unsupervised pre-training or continued pre-training, you might do that for like one epoch on a couple tens of GBs. Like you wouldn't do that on terabytes. Once you have terabytes, then you're looking at pre-training from scratch, which is the next class. But for continued pre-training, yeah, you'll do a couple steps of domain adaptation. And then once you've done this, you can then fine-tune it. So then you can fine-tune it for different downstream use cases, and it will know your data very well. Like once you've done both continued pre-training or domain adaptation and like some small scale fine-tuning, that's going to be a really powerful model. So, but it's hard, right? There are more data sets you need and a little bit more skills. So there's a spectrum of fine-tuning techniques. And so parameter efficient fine-tuning, again, is a new library from our friends at Hugging Face, which lets you fine-tune only a few parameters. So literally, let's say you have this massive 175 billion parameter model. This thing is multiple hundreds of gigs on disk. You need like at least 16 GPUs to hold this thing in memory, maybe more. or accelerators. And you don't want to train this whole thing because you need a massive data set to do that. And then you'd have to store the weights, and it's a big pain in the butt. And so what you can do is use LoRa to inject trainable weights. So LoRa is actually gonna, which is a part of Hugging Face, it's actually gonna inject these trainable weights into this model and then fine tune just those weights. So it saves you from needing to train this massive model because you can just fine tune it in this super parameter efficient way. Here's a view of doing that from our friends at Hugging Face. So again, you're going to import from this transformers library, import this auto model for sequence to sequence, and then PEFT. Yeah, so transformers is of course the Hugging Face library. PEFT stands for parameter efficient fine tuning, and it's a new library from Hugging Face. And so from this PEFT, we're going to get the config, the model, set LoRa, and the task type. And then here we can point to Big Science, so we're pointing to their Big Science blue model, MT0 large. You want both the model name and the tokenizer. And then we'll set this LoRa config. So we have our LoRa config, we'll set the task type, sequence to sequence. So we're doing possibly some type of translation here. And then inference mode, LoRa, and then this dropout, some tunable parameters. We load the model. So we're going to take this whole model from pre-trained, and then we're going to pass this model that we picked up from pre-trained, which again, the pre-trained, that can point to the Hugging Face hub. So that's just literally downloading from the hub, which is going to be slow if it's a really big model, or maybe you already downloaded it and so it's just sitting locally, and so you just pass this local path. So you pick it up, and then yeah, you've got this. Then you're going to pass the model to this PEFT function, right? So get PEFT model, which we imported from their library. We're going to load that in here. We pass it with the config. So it takes both the model and the config, and then you can see which parameters we're going to train. So get trainable parameters. So here we are out of all of the parameters, right? So that's about 1.2 billion parameters, right? Because we have 3, 6, 9 spots, so about 1.2 billion parameters. And then of those we're training 3, 6, we're training about 2.3 million parameters, which is just under 20% of the model. So that's an extremely efficient fine-tuning.
All right, let's check it out in a demo. So in this notebook, we are fine-tuning a GPTJ 6 billion parameter model. And actually, we're going to use the SEC filings from Amazon, believe it or not, and we're going to fine-tune this model to better generate natural language that looks like SEC filings. And so, same as last time, the notebook is available in the SageMaker examples. SageMaker examples, that's right here. Intro to Amazon Algos, Jumpstart, and then we're going to run this guy. As before, here's your bit.ly, which you can use if that's easier. Alternatively, feel free to use the QR code. So with that, let's get moving. And so, believe it or not, I do have this notebook up and running myself. And so this is, again, as usual, on SageMaker Studio. I've got all sorts of instances running today. So I've got a CPU machine. We got a C5 here. You know, I've started to see it more common to have notebooks run on M5s. So M5 large, M5 8s. I think the small machines like your T3 medium is just it can't always bear the weight of all the compute you're trying to run. So just starting with something a little bit larger, like the M5 is seems to be a good bet. So in any case, so we're on Studio, and we're using our SageMaker Jumpstart as usual because all the images are pre-built and we get to interact with it very easily. Now, this notebook is nice for a couple of reasons. It has a clear before and after. And so the before is simply looking at the model. So we're going to pick a GPTJ 6 billion parameter model, and then we're going to host this model. and then through hosting, we will see how well it performs. So we'll get some sort of base performance on that, and then we'll fine tune it, and then we'll see how well it does on the same prompts. And the response is pretty wild, actually. It's obviously much better after it's been fine tuned than it was before. So that should be good to see. And then on top of that, we're going to do hyperparameter tuning, actually. So there's an hour-long job in this notebook that tunes this model using a variety of hyperparameters, and it turns out really well. So let's explore this. So we're using the SageMaker Python SDK, etc. Porting this name from the base, life is good. Picking up the URIs, retrieve the model URIs. So what's happening here is basically we are telling SageMaker from the name of this model, from this model ID, which is this Jumpstart example, we grab the model image. So basically we can point to like the Jumpstart SDK, basically. Or through the SDK, we point to these Jumpstart sort of pre-built examples, the pre-built images, and then we're just going to retrieve those. So we get the model URI using this .retrieve, and then we'll do the same. So that's the URI. That's actually the image that we'll use to host the model, and that came from the model ID, and then the version, and then there's a scope here, which is inference. So this means you can point to Jumpstart to just get the hosted version of this model. Alternatively, you can do that for just the training version of the model. And so we'll create this SageMaker model. You've probably seen this before. The image, model data, which should be in S3. My apologies. So yeah, so the deploy image URI is the script. And the model URI, that's the actual data for the model. That's like the model weights. Right? AWS role, and then the predictor class that we want, and then the endpoint name. And then we create this. Fortunately for you, I've already done that, so we can check this out over here. Actually, so we're going to go up to the home, and we'll go down and we'll look at deployments, and we'll click on endpoints. So I have quite a few endpoints. I was running on some Inferentia 2 with Stable Diffusion, and this is the Jumpstart example, which we can look at. Yep, so Hugging Face, text generation. Interesting. All sorts of other metrics for us. Great. So we'll go back out here. Now we're going to query this endpoint, and then we'll walk through the response. So we're going to query the endpoint with this JSON payload, and then parse the response back. So we'll set parameters, max length, number of return sequences, and then here are the prompts, basically. So we have 3 prompts, and we want to see what a generic GPTJ 6 billion parameter model comes back with. So let's... And it's not pretty, right? The intention is that this is a garbled mess. Like, this makes no sense. This is clearly not a high quality output. And so at this point you're thinking, like, what is this model about? Why do I care about this? What's shocking is that by the time we get to the end of this notebook, the quality that this returns is amazingly higher. Like, it's so much better than it was previously. And so we'll actually show you how to do that in this notebook. All right, so now we're going to fine tune that pre-trained model on this new SEC data set. And this is actually, I like this because this is actually unlabeled data. Actually, I'm not positive about that. Let's see if we can figure this out. So this is a sample of the data set itself, the text file. This appears to be unlabeled. So my expectation is that we're actually doing domain adaptation, as they call it. So in NLP, we actually mean this as a continued pre-training. So this image is going to continue pre-training the GPTJ 6 billion parameter model on our SCC data. And so that's why we can do this without explicitly needing to label the data. We don't need to organize it into a positive and negative sentiment or questions and answers or really any of the low-level labels. We can just take the raw data just as it is and then do pre-training directly. And so we'll do that continued pre-training in this notebook here. So we'll retrieve the training artifacts. So this is the training image. All right. So we got this. Then we're going to set the parameters. And then, yeah, 2 types of parameters. So one type of parameter is for the training job, which is obviously basic things like the training data path, output path. And then for the algorithm, we have hyperparameters for that as usual. So your data bucket, prefix, S3 paths, life is good. And now we're going to set some hyperparameters here. So a per device train batch size. So this is telling us the number of batch sizes per GPU. Actually, so per accelerator in the training cluster, that's the number of objects we'll use. And then, this is nice. Yeah, so we can grab all of the default hyperparameters for this model, actually, just by retrieving the default. That's really handy. Very cool. So we'll grab the defaults, and let's take a look at these. So we have epoch, learning rate, per device, warm up, instruction tuned false. Good to know. So this base model has not been instruction tuned. Trained from scratch, false. Interesting. I'm curious about that. All right. And now we're going to use automatic model tuning. So here, we're going to update AMT in just a second here. And then we have the range of hyperparameters. Maximum jobs is 6, parallel jobs is 2. And then we'll train this. So we're setting the estimator, all the rest of our configs. Here is this training image. Source directory, entry point script is out here. So that's in, yeah, here. So in the SageMaker example still, and then it's in Introduction to Amazon Algorithms. So out here, and then, where are we again? There we go. Jumpstart Foundation Models, Domain Adaptation. So Jumpstart, Foundation Models, here we go. And then this guy. So where is this transfer learning script, I wonder? I am not certain about this. Train source URI. Let's see if we can unpack this. So train source URI is in S3. Ah, interesting. Okay. So Jumpstart actually has this training script stored in S3. So we basically, it's completely abstracted. We don't have to touch it in the slightest. It's already ready to go, which is pretty cool. All right, great. So that's where this transfer learning script is. It's parked in the Jumpstart S3 bucket. And then this is our instance. Let's see what our training instance type is. Maybe that was listed above and I just missed it. So the training instance type is a G5. Okay, so a couple GPUs, nothing crazy. And then we have this hyperparameter tuner. It's surprising that this still took an hour. I thought this was using AMT. Yeah, okay, so it still takes an hour even without using automatic model tuning. So that must be because it's actually fine-tuning the entire model. It's not even using a like a parameter efficient fine-tuning, which is surprising, certainly. But don't get me wrong, the results are great. So you'll be happy once we get there. So we call model.fit, and then the job runs. So remember, while your job is running, you can right-click on this and then enable scrolling for outputs. And then that makes it much less likely for your notebook to crash, because then everything is sort of nicely tucked into the scrolling bar. Yeah, there we go, great. So remember to do that. And here, so let's look at the job in the console, actually. Zoom out for you. So in the console, yeah, here is this one job we ran. So one jumpstart text generation model still took a solid hour. This was really just one job. So this was an hour for this one G5.12 to churn through our data set. Let's see where the data is, actually. Okay, also in the jumpstart bucket. Okay, interesting. All right, so in any case, you can run this through using automatic model tuning, or you can run it without automatic model tuning. Both are fine. And SageMaker has this nice training job analytics. So after you've listed the job name, we can load up a data frame, actually, with the analytics for that job, which is nice. And so in this one, we'll pick the best model. Actually, it's the best one that's loaded here. Notably, it was just one job. But in any case, we're going to deploy this. So now we'll deploy onto another G5, and we'll use the same software framework we've been using previously. So images, image.uri, we're going to retrieve, skipping the region of the framework, because we'll pass the model ID, the model version, and then the instance type. Especially CPU or GPU matters, and then it of course matters for what accelerators you're using and things like this. And then the scope, so inference versus training. We'll get a new endpoint name, and then we'll create this fine-tuned predictor. So we create this fine-tuned predictor, and then we can validate that that indeed exists. So that's out here. Here we go, up in the top with the little house. We'll click on endpoints. We'll close that out. And then this should say, oh, I guess there are two. Yeah, Jumpstart 1, Jumpstart 2. Okay, perfect. Great. So we have two Jumpstart models, and then now we'll interact with this. So we'll query the endpoint with the JSON payload and then parse the responses. So we have our same parameters, top K, top P, temperature, and the same prompts. So this 10K form, this form 10K report shows that we serve customers through, our vision is, etc. So we're going to send those prompts to the model, and then bam, check this thing out. So I mean, this looks so good. This looks so much like the SEC reported data. It's amazing. It's so detailed. Wow, it's incredible. Yeah, so this is the difference. Remember, we saw this, and then here they have it in this nice little data frame for you. So these are the prompts. And then this is before fine-tuning, which is this garbled mess. And then after fine-tuning, we get this extremely clean response. And so in this notebook, we see that fine-tuning even a very small model, so fine-tuning this GPTJ 6 billion parameter model on a extremely specific data set, such as the SEC filings for Amazon, can generate really powerful results. And so with that, I hope you enjoyed this video. In the next one, we are going to take a look at pre-training foundation models, actually. So in the next video, we're going to learn the first part of what you need to pre-train a new foundation model. It's like a part 1, and then the part 2 is going even deeper and preparing data and then training at scale. So I will see you there. Thanks.